going to start with a statement that I will not spend any time supporting, but you've heard this many times before. Lambda CDM agrees really well with the observed large-scale structure of the universe. And so that's the pie chart you've seen very often, leading to predictions for the large-scale structure here. Right. And on large scales, it is really hard to get around this. CDM is the right description. Right. There's just so many things it gets right that if I had to like build another model and cross these hurdles, it's just hard to imagine that jumping through all these hurdles without falling down at some point. Right. That's sort of the starting point, which is that a theory with cold, non-interacting dark matter does right, is the right description. But then when you go to smaller scales and you start asking, how cold does the particle have to be, or does the particle really have to be non-interacting? That's when interesting things happen. That's when you realize that you can make sort of a wholesale order 1 change and still keep all of these successes. No preamble. I'm just going to jump into this. Right. The dominant view in the past in terms of dark matter has been thinking about supersymmetric sectors where the lightest supersymmetric particle is really the dark matter, right? And that might still be true, that a small fraction of the dark matter might still come from that sector, but people have since then expanded their ideas about the dark matter. Some of it has to do from top down, like thinking about new ways of producing dark matter, in general thinking about physics that gives rise to dark sectors. Some of it has to do with the fact that we haven't really found the dark matter we are looking for. And so dark sector particles have, if you talk to a lot of the young particle physicists, these are dark sectors are things that we play with, right? And they're not very mysterious things. For example, I would classify a sterile neutrino as a dark sector dark matter in the sense that, it is physics that's accessible in terms of astrophysics, but it's separated from ours by some really high scale physics. That's really sort of in a broad brush way what I'm talking about. And so when you have a dark sector, there's no real reason specifically to pick a dark matter particle to be at the TeV, 100 TeV scale. It could be light. And as soon as you say those words, you realize that the dark matter can interact with itself, right? There's really nothing prohibiting it, right? So that's sort of the basic motivation, is that we really have a very good idea about dark matter and how it interacts with the standard model. We can constrain it very well. But when it comes to the dark sector, the dark matter interacting with itself, we really have no constraints. The things I'm going to show you are really the only way to get at it. All right. So, when I talk about SIDM, essentially self-interacting dark matter is CDM on large scales, in the sense that it'll give you back the same CMB, it'll give you back the same large scale structure. So anywhere you ever read in a paper lambda CDM, feel free to replace it with lambda SIDM. Right? You can construct a model that has identical, and you don't have to jump through any hoops to do this. It's a particle. Essentially, the only difference between the cold dark matter and SIDM are these interactions, and interactions between the particles really don't do anything to change the large scale structure. Now you can build models where the dark sector, because of the way it is set up, changes the power spectrum, but those happen on pretty small scales. Okay, and I'm not going to talk about that aspect. It's a very interesting aspect, but that's sort of more cosmology. This talk is more about the astrophysics. All right, so here's my model for you. It's a model that's actually motivated by the phenomenology of rotation curves, and I'll go into this more in just a bit. Like I said, the original SIDM phenomenology was proposed by Spergel and Steinhardt. The thing I'm going to talk about is a very specific incarnation, a realization of that. And it says basically that, at low velocities, So velocity is accessible in galaxies, so tens to hundreds of kilometers, 100 kilometers per second. The cross section of interaction over the mass of the dark matter particle is a few centimeters square per gram, right? It's essentially of order barns per GeV. So if your dark matter particle is a GeV mass, then the cross section is a barn, right? So it's a big cross section. Right? It's close to the nuclear cross section, as I'll allude to in just a bit. But this cross section cannot. Okay, so the reason why I'll show you why this is interesting is because when you allow for this cross section, you actually get very simple predictions for the dark matter halo, and it fits galaxy rotation curves really well. Okay, and again, I'll go into this in some depth. The other reason I actually like this is because these cross sections are large enough that the scattering time scales become short enough that the dark matter gets driven to equilibrium, and they get driven to equilibrium quickly enough that they become insensitive to the star formation history. What does this mean? It means that the final dark matter distribution depends on the baryon distribution at the end, and not so much how you actually brought the baryons together. Again, we'll talk more about this. Now, this is not true for all SIDM models. Like if you knock down this cross section, then this is not going to be true because the time scales are not going to be fast enough. But when you have cross sections of order few, 3, 4, 5, and it could be much larger. It could be 10, 20. Then this is true. But also, you cannot have this cross section be velocity independent, and that's the really exciting part in terms of model building. This cross section must fall with velocity because we know from observations of clusters, okay, and it's not the bullet cluster, it's measurements of the densities of clusters through lensing, for example, and kinematics. We know that the cross, you cannot support a cross section that's that big. It's just completely inconsistent with clusters. So by the time you go from 100 kilometers per second to a cluster, which is 1,000 kilometers, couple of thousand kilometers per second, the cross section must fall. That's the only way you can build a viable model. Now, this might seem, where did this velocity dependence come from? Let me just give you a motivating standard model example. Okay, this is just the scattering, a plot of the scattering cross section for protons and neutrons. Alternately, you can just think of it as neutron-neutron, collisions. On the y-axis is the cross section. On the x-axis is the incident energy in MeV. All right. This is 20 barns. This is the famous 20 barns nuclear cross section. And if I were to think of this as dark matter scattering, so for a moment imagine that the dark matter particle, the dominant dark matter particle, is just a stable hidden neutron. So a stable dark neutron. Imagine a dark sector where there's a neutron and it's stable, right? In the standard model, for all we know, the fact that the neutron is unstable and the proton is a light is an accident. Right? You could just easily switch this around in the dark sector. Just imagine it's a neutral particle in the dark sector that's stable. And if this was the way it interacted, right, just scattering, all this is pure elastic scattering, then in clusters you would be accessing velocities here. Right? These incident energies turn into like 1,000 kilometer per second velocities. Right? So bullet cluster and things like that, like the Muskelbot cluster, which are these merging clusters, you would be accessing velocities in that range. Rotation curves would be sensitive to velocities here. Right? So you could imagine taking different objects from dwarf galaxies to somewhat larger galaxies to clusters and actually getting this curve. Right? And surprisingly, actually, this curve does a pretty good job. Probably I would shift this a little bit to the left, but other than that, a neutron-proton, just a nuclear cross section. So just a geometric concept. Is this a geometric? But of course, here it's not geometric because now you can, there's the binding energy of deuterium, right? So this starts falling because you have enough momentum. But yes, this is essentially just coming from the neutron-proton cross section, right? So in terms of model building, what do you need? Well, basically you need two mass scales to build in a velocity dependence, okay? One of the mass scales is just the mass of the dark matter particle. That's there in every single model, right? The other one is what sets the velocity dependence. So yes, this would be related to the pion mass, but it's not. It's not just QCD, right? I mean, this is nuclear physics, so um, yeah, it's more complicated. Yeah, yeah, it's related to it, but it's a more complicated calculation. All right, but you know, if you're just thinking of just an elementary fermion, then there's some mediator of the force between them, and the mass of that mediator divided by the mass of the dark matter essentially sets the scale of the velocity dependence. So if the mediator mass of the dark matter mass is, let's say, 10 to the minus 3, then when V over C is about 10 to the minus 3, which is Milky Way, you would start seeing a velocity dependence. Right? You would, the cross section would start falling. Right? So this fall here is is related to, again, it depends on what the model is. If it's, like I said, a simple Yukawa potential, then it's related to the mediator mass over the dark matter mass. You could have something else like a dark sector atom. Imagine that the dark matter is like the hydrogen atom. In that case, it's the ratio of the electron to proton mass. Right? So you need two scales in the problem. Right? That's what I'm saying to build this in. And this is not, you don't have to bend over backwards. It's just there. You know, if you had a hydrogen scattering, you would have this. Basically, the curve would look the same, but just shifted in energies. Right? So velocity dependence is not something baroque. Just think of it as something part and parcel of the model you're building. The one example where you might get a scattering where you will get a scattering that's velocity independent is if, for example, the pions are your dark matter, a dark pion, and they are mediating through pion exchange. That's essentially going to be velocity independent. All right, so there's no dearth of models like this. All right, and I like this. Maybe there's something to this similarity between what I want here for rotation curves and what we have in our own standard model, which is the nuclear cross section of order 10 bonds. Right? So, remember, this is, the QCD scale is not something you need to put in by hand, right? It comes, from this running of the coupling constant when it actually becomes really strong, right? The 100 MeV scale sort of falls out of it, right? So there's something very neat about the nuclear cross section. So I kind of like it for that reason, right? Maybe this is a clue that there's a QCD-like structure in the dark sector. Nature's done it once, why not twice? All right, so first I'm going to talk about how this model I presented, the simple model of just elastic scattering and nothing else. So imagine that the dark matter does what cold dark matter does, but in addition, scatters off of each other elastically. What does it do to galactic halos? So here's the one slide you need to understand this. There's two plots here. This plot is telling you about sort of the effective temperature. So it's the RMS velocity of the dark matter in a halo plotted against the radial distance from the center of the halo. They've been both scaled by some typical velocity. So Vmax is the maximum circular velocity you would get in that halo. And RS is related to where that maximum happens. Okay, so the maximum would happen at 2 times, roughly speaking, RS. So what this is telling you is that so the black points are CDM, cold dark matter, so no elastic scattering, right? And so you see this familiar feature, which is that the inner part of a cold dark matter halo is cold. That's how you stuff more and more particles and you get the central density cusp. And then it's sort of like gradually plateaus out here. Roughly speaking, it's kind of isothermal out here. What happens as you crank up the cross section? So at 0.1 centimeter square per gram, nothing much happens. You can sort of see some changes here. But when you have 1 centimeter square per gram, what's happening is, because of these interactions, right? Now remember what's happening is, dark matter particles are on these long on these orbits, right? So you have particles coming from the outside interacting with particles in the inner part. And eventually, if the outer part is hotter than the inner part, you'll start transferring energy inside. Right? There's a gradient in the temperature, think of it that way. And there's an effective transfer of energy from inside out. And so over time, and this is after 13 billion years, you can sort of see that for 1 centimeter square per gram, the inner part has become isothermal. That's basically it. Right? All you've done is what hydrogen atoms do in this room. Right? They scatter off of each other and equalize the temperature. But it does something pretty interesting in a galaxy, unlike this room, which is when the scattering happens, since you transfer energy in, the particles here that gain the energy move to orbits that have longer apocenters, right? Whose apocenters are further away. And so you push particles out in this process because you're dumping energy into this. Right? And you can kind of see that here. You sort of start out with this cuspy profile. So this is the density as a function of radius. And then as you transfer energy in and get isothermal, you've taken this mass here and pushed it out here. So you can see that there's more mass here in the SIDM than this. And you make a pretty big change to the density in the inner part. Right? So you pull this down. Now this is interesting because it sort of creates cores. And this might be something that's that when you look at data, you can prove or disprove. But if this were the story, this model would be dead. It would be pretty uninteresting. Okay, the story is actually a lot more interesting, as I'll try and tell you now. Okay, so I want to pause here and ask, are there any questions about this? Because we're going to just use this and not much else for the rest of the talk in terms of the physics. So the inner part.
Certainly there are baryons.
Yes, which is the next slide, okay. which is the critical part about it. If it wasn't for that, then I would say, like I was saying, this wouldn't be a working model. All right, so I will divide up this region into, this is sort of a very simple picture. We can think of a region that's isothermal in here. Sort of this region in. And then the outer part where the scattering's sort of been really ineffective. By the way, the scattering cross section is big, like 10 barns, right? But out here in this region, most of the halo has barely interacted. So this is sort of the region where you had one interaction over the edge of the halo. Right? And that's just because the dark matter is so diffuse. Right? So even with this big nuclear cross section, most of the matter, 90% of the matter outside, has not really interacted. Right? But in the inner region, they've interacted. So that's the inner core. Okay. So in the outer part, it'll look like the cold dark matter, which is this Navarro-Frank-White profile. In the inner part, it'll be isothermal. So very simple model. And this is where the baryons come in and makes it really interesting. It's kind of amazing how simple it is. I mean, this is like StatMech 101, So the inner part is isothermal. But what does that really mean? It means that the distribution is Maxwellian. Right? That's what the scattering is going to do. It's going to make the distribution inside Maxwellian. Well, Maxwellian, you know what it is, e raised to minus e over kt. Integrate out the velocities, the kinetic energy, what are you left with? Just the gravitational potential. Right? So again, basic StatMech tells you that in the inner part, once you equilibrate, right? If the time scale for scattering is fast enough, then the density profile of the self-interacting dark matter has to look like e raised to minus the gravitational potential over kt, where kt is the temperature, right? And what is the temperature? No, the temperature of the dark matter. And that's essentially just, this VRMS. And what is VRMS? You can kind of see it's like 1.2 times Vmax. So it's been just set by the maximum circular velocity of the halo. So you pick a halo, you see what its circular velocity is you basically know what the temperature is going to be for a large enough cross section.
So what if you have some admixture of CDM and SIDM?
Yeah, now you're asking a hard question. Then you have to factor that in. The temperature will depend on both the CDM and the SIDM. So the temperature depends on everything that's inside, all of the matter. That's a good point. All right, so phi over kt. But this phi, remember, is the gravitational potential of everything that's inside there. Doesn't matter whether it's dark matter or baryons. So in particular, if you have a galaxy where the baryons dominate the inner part, like our Milky Way, then the density profile of the dark matter will just follow the potential of the baryons. It's pretty neat, right? It's exactly the opposite of what everyone had predicted when they first did these simulations, which is that when the scattering happens, the dark matter is just going to become puffy and spherical, right? But that's not what happens, for example, when baryons dominate. In the Milky Way, the dark matter in the central part of Milky Way in SIDM is shaped like the potential of the Milky Way, which is sort of like a squashed, right? So it's actually squashed. It's not spherical at all. And if you actually do this for the Milky Way, simulate it with a Milky Way disk in there, then the density profile of SIDM is basically like that of CDM or even a little bit higher. So there's no real core in this, right? Which is, and it's all got to do with the baryons, right? Now, if my cross section were not that high, then I would not be able to make these predictions with any great degree of confidence, because then your results will depend, as it should, on the feedback. It'll depend on what the baryons are doing, right? But here, what I'm saying is, you give it 1 billion years or so, the equilibrium solution will you have to get to the equilibrium in that time, and then your solution has to look like this. I don't care what happened before that. It only depends on the final distribution of the baryons. That's why I went to this part of parameter space where the cross section was large enough, because
it's the potential, total potential.
It's a total
not
potential.
Just where the baryons are.
No, it's
also where
absolutely.
the dark matter
Yeah,
is.
so you have to solve it.
So you have to,
Yes, yeah. But I gave you just an example of the Milky Way where in the center it's dominated by the baryons. But in general, that's not true.
in a dwarf spheroidal or something, it might not.
So in a dwarf spheroidal, it'll be the other way around, which is the baryons are unimportant,
Right.
and then you do get a core. And in that case, there's a very interesting thing, which is there's no new scale in this problem with a large cross section. The only scale in the problem is this RS. And that's because when the cross section is fairly large, you basically become isothermal all the way out, right? So your core that you create is basically of the same scale as the NFW scale radius. So in a strange way, this is basically, everything is determined by just the cold dark matter properties, by RS and rho S, or Vmax and Rmax, right? So yes.
One question. So all this is, I think, is predicated on the assumption that the dark matter self-interactions just redistribute energy. There's no real dissipation.
In this model, there isn't one.
Yeah. So, for example, I could imagine a dark sector where you emit some light particle.
Absolutely. So we've looked at, for example, yeah, absolutely. So for example, like we've looked at what if it's a dark hydrogen atom, in which case there's the analog of the 21 centimeter line, and that'll allow dissipation. Or in clusters, you can have interactions where you bump up an energy level and then scatter back down. So it's possible to do that. Depends on the model. But the thing I'm presenting to you right now is just the simple bare bones only scattering.
But if you allow dissipation, so I can change the phase space density for the self-interacting dark matter, then that's a player in the way that baryons are, and so that will end up dominating the potential at.
Yes. So if you allow for dissipation and if you allow for cooling, then it'll certainly change the solution. But I don't know. I haven't written down a model where the cooling is that important. All of the ones I've looked at, the cooling is at the 10% level at best. But it's possible. People have looked at this. There are other simulations with cooling, like Mark Fogelsberger has done a few simulations. Tracy Slatier, Mark Fogelsberger, they've looked at this. Right. So the only other thing you would need to remember is that there are no new parameters in this model. It's only the NFW or the cold dark matter parameters, and that's because there's two free parameters here, T and rho naught, right? But they're not free because you want this model, you want this profile, which is isothermal, to smoothly match onto the outer profile. right? So whatever is the outer profile, that'll determine what happens in the inner part. Right? So just like in CDM, there's two free parameters. In CDM, typically we take that to be like, Vmax and Rmax, and those are the same free parameters. Okay, so there's no new free parameters when you're fitting to halo profiles. All right, so let's look at. So there's one more bit of physics before we move on to showing you what it does to rotation curve, and that's a very interesting bit of physics, which is, let me just go back to this figure here again. So this thing became isothermal, right? Now imagine running it forward in time a little bit more, right? This whole thing is it's getting isothermal in the center. What happens now? So remember, initially, my entire argument was based on transferring heat from outside in. Now when this is isothermal, right, you're no longer transferring heat from outside in, right, because this part is hotter than the outer part. Over long time scales, you will start transferring energy from inside out. Right? So you're transferring energy from inside out, which is you're cooling these particles, right? But since this is a gravitational system, what's happening is these particles get, they basically get into smaller orbits, right? So you concentrate them more towards the center. That increases the gravitational potential. That makes it hotter, right? So as you cool, you get hotter gravitational systems, right? It's a negative heat capacity. And so what will happen is this will start getting hotter and hotter. You will keep transferring more and more energy outside, and that's a gravothermal runaway process. So all SIDM halos will eventually go through this gravothermal collapse and turn, in principle, into black holes. Yeah, this is something very interesting, but yes, there is this prediction that every SIDM halo, given enough time, will host a black hole at the center. Right? But you'll see how this can get accelerated towards the end of this talk. All right, so here's a concrete, simulation. Instead of running time forward, here what's been done. So this is from James Bullock's group. What they've done here is they've run different cross sections. So for people at the back, this is 0.1 centimeter square, 0.5, 1, 5, 10, 50. So 0, 0.1, 0.5, 1, okay, and then 5, and then look at what's happening to 10. The density starts increasing. And then 50, the density's gone up, right? So this is the core collapse process. Right? So time, instead of running, this has just all been run for like 14 billion years. Instead of running it longer, it's just you just run it with a larger cross section, which is basically the same thing. Okay? And so eventually you go through this process where you create a core. The core gets as big as it can get, which is of order RS, that scale, and then you start core collapsing. Okay, so this is a very generic process, and here's a more semi-analytic model where you see this. This is an estimate of the core density in units of sort of the NFW scale density. So that's the typical density of the halo, cold dark matter halo. And here is an estimate of the time in some scaled units. And there's a whole bunch of cross sections here. Really doesn't matter. What you see is there's a common envelope where they all get diffuse and less dense in the center. And this part is where you're here. You have this big core. And then eventually they start core collapsing. And then we've switched the scale from logarithmic to linear scale here. So that's why you see this discontinuity. And it just goes, right? Because it's, basically this process just is a runaway gravothermal collapse process. Okay. Now for reasonable cross sections, or for cross sections we've been considering like 5 or 10, this doesn't really happen in field halos. This period is long enough that you're always stuck here. Okay. So this dot tells you for each given cross section where you would be today. So you can say that for 5 centimeters square per gram, you're sort of at the bottom of this. You're not core collapse. But if you're at 10, then you're kind of maybe starting to core collapse. Right? So unless you're looking at cross sections that are very high, you would think this is irrelevant. It's actually not. Hold on to this. I'll come back to this at the end. For now, just remember the thermalization I told you, the e raised to minus 5 over kT. Okay, so the thing I want to do in this talk is basically just give you a quick glimpse on what this does in field galaxies, and then just maybe tell you a little bit about satellite galaxies at the end as a way of like really maybe falsifying this or ruling it in. All right, so rotation curves. You've all seen examples of rotation curves. Here's you know, just an analytic picture of what happens with rotation curves. So what's plotted here on the y-axis is the circular velocity due to the dark matter as a function of radius. So let's just focus on the top plot. Here I've assumed sigma over m is 3 centimeters square per gram. Picked a certain halo with a maximum velocity of 70. And this band, this gray band, is the prediction of the NFW profile. Okay, and the band is coming in because of the merger history for any given Vmax. There's some range of possibilities of inner density even within the CDM paradigm, right? So you remember that halos in cold dark matter are one parameter with some scatter. That's one parameter, and that's the scatter. Now you turn on the cross section, what happens? Well, it kind of looks basically like CDM, except that you have this similar scatter, but the density in the inner part has gone down, and that's the formation of the core. You've taken mass from inside and pushed it out, so you get this core. Okay. What would happen if there were baryons in there? So here's a plot with the baryons. And the baryons are now put in this is just an analytic model. So you take a certain stellar mass, in this case is what, 10 to the 10, and then you say that, well, this forms a disk, exponential disk of scale length 2 kpc, 3 kpc, 6 kpc. Okay, and then the orange would be a case where there's no baryons. So this orange sort of matches up with that. Then you add some baryons and you see that the density has gone up. Then you make the baryons even more compact. So you're keeping the mass of the baryons fixed, but you're making it more compact. And what you see is like the density jacks up. And here's a really compact disk. And you can see what's happening here, right? There's so much more dark matter in the center that the rotation curve rises really quickly, right? And that's just the e to the minus 5 over kT. If you dump more baryons in, if you make it more concentrated, the potential goes up for just the baryons, and that forces the dark matter to be way more concentrated in the center. So as you make the baryons more compact, the dark matter becomes more dense. Right? So even without doing anything to the baryons and even without coupling the dark matter and baryons, just gravitationally, the two are coupled in this in a very intrinsic way. The baryons tell dark matter how to behave in these models. And this is just completely gravitational. And remember, it's coming about because the cross section is kind of large. Right? Now, how does this fit? How do you see? How does this fit galaxies? So I'll just give you 3 examples. Okay, and there are 3 really good examples. There's a lot of curves in here, but let's first focus on the data. So again, this is a rotation curve for 3 different galaxies. All of these galaxies asymptote to similar velocities. See that? It's 80 kilometers per second. Here, in this galaxy, you get to 80 kilometers per second within about a kpc or 2. Okay, so this is very concentrated in stars and dark matter. Here, the rise is much more gentle. Look at the scale. And here, it's even more gentle. Okay, so 3 galaxies with similar amounts of baryons, roughly similar amounts of dark matter in the outer parts, but behave completely differently in the inner part. What's the difference between them? Well, look at these purplish lines. And in particular, look at the thing that I've denoted as stars. Here, the stars are distributed in a very diffuse way. So this would be a low surface brightness galaxy. Here, you can see this is a prototypical high surface brightness galaxy. It probably has a small pseudo bulge in the middle. And you can see that the stars are like very dominant in the center. So in this case, what's happening is that the dark matter, the SIDM prediction is essentially like this, is the same as the NFW halo, right? It's in this case, what SIDM says is because there's so many baryons in the center, the dark matter, because of the e to the minus 5 over kT, has to be really, you know, dense in the center, and that's being shown by this blue line. That's the halo. Okay, this would be the case if you just neglected the effect of the baryons. Huge difference, right? And this difference is coming about because of the potential of the baryons. Whereas here, the dark matter, you know, has this sort of big core and rises very gently. Right? And this is not a unique case. Essentially, every time you actually see galaxies that are this diffuse in stars, it's also diffuse in dark matter. Right? So where you've heard these things, you know, that the core cusp issue, right? The issue is not really about cores and cusps. The issue is that, you know, there's both cores and cusps in the data. And the galaxies where you see these big cores, from what we have looked at, are always cases where the stars are very diffuse also. So the stars and dark matter are linked together, okay, in this way.
Have you put the straight CDM model, is that the dashed purple line? Or?
Yeah, it's this thing here. But I'll show you a comparison to the CDM in a statistical sense in a bit later. Because
How are the gas and the stars coupled? So in that first panel, for example, do I interpret that as the gas has been converted into stars?
are you asking if they have the same amount of gas? I mean, in this particular case, it has roughly similar amounts of gas.
About really star formation history. You said it's not terribly relevant, but it would be relevant for a number of other issues, like what the abundances are, for example.
Yeah. So I'm not sure what the question is. I mean, I don't know in particular.
In that one,
yeah.
The star density near the center is very high compared to the gas density.
Yeah.
So I'm wondering what that means for star formation.
I think it's a good question, and something I'll come back to is, like, you know, what is the difference between these high surface brightness and low surface brightness galaxies, right? Why do some galaxies form as low surface brightness, and why do some form as high surface brightness? Although this is, I probably won't really talk about this in SIDM. The only way you form these sort of like very diffuse and, you know, galaxies is by putting them into very low concentration halos. So these have to be galaxies that formed very late in the universe, and they are low concentration because of that. And that's the way you would get these like very big and diffuse things, right? So it's in principle a testable prediction. It's something that I'm working on now, which is that, you know, you expect sort of the most diffuse galaxies to also have formed kind of late and be in these low concentration halos. They must be super rare. They can only be like 5–10%, and that's very consistent with these kinds of systems. It cannot be more than that. Yeah. So, for example, when we did these fits, we were very, very careful about asking, like, how many of these 2 sigma, you know, minus 2 sigma things do you have? And out of the 100 or so fits we did, it was like, you know, 5 to 10. So yeah, you know, the statistics would be interesting to do. Anyway, here's a compilation of about 140, I forget exactly how many, but it's about 140 galaxies. And they're color-coded in a way that tells you something about their surface density. So the panels are essentially telling you about the maximum circular velocity, so something about the size, the mass of the galaxy. So here's about 80 kilometers, 100 plus, 150, and then these are getting to be Milky Way and bigger, right? And then the color coding here is that blue are very compact galaxies, and then the reds are sort of more diffuse, low surface brightness. And you can sort of see, it's not perfect, but you can sort of see a sense in which, you know, the circular velocity rises really quickly there and not so much there, right? And the lines are the SIDM fits. Right? And in every case, we've tried to make sure that the fits are within sort of this 2 sigma scatter you know, that's allowed for in hierarchical structure formation.
You don't allow yourself to change the cross-section.
No, this is just one cross-section. Yeah. It turns out that you know, because of this equilibrium, it becomes very insensitive to the cross section. So I could take it to be 3 or 4 or 5 or 10. Doesn't really matter. You'll get back the same thing. Yeah. Yeah. Even in the small ones, it's difficult. I don't know. I mean, at 10, maybe there's core collapse happening, so it might change. But between 3 to 10, they're all sort of off order RS. Right? And that's just simply because, like, once you get out to RS, the NFW halo is already isothermal. And so you don't really change the core size that much by jacking it up. At least in the fits we did down to, like, 50 kilometers per second, we tried, I think, 3, 4, 5. It didn't really change anything. They look pretty much the same. In any case, for this one, we just fixed it to be 3 centimeters square per gram. All right. We'll talk about this in 2 slides, okay? Actually, after this one. So here's just this is for the aficionados. Here's what went into the fits. So this is showing you the Vmax Rmax relation. This is the Dudden et al. Relation for Planck, and that's the 2 sigma scatter. And I'm just showing you that all of the fits we did lie within that. This is the stellar mass halo mass relation, and this one's the Baruzzi's fit. You can sort of see that they all look reasonable, nothing untoward. This is the baryonic Tully-Fisher relation, and the orange points in the background are what you would get for a Mond-like fit. Again, they look perfectly reasonable, right? And they're all coming from this very simple idea of something being isothermal, e to the minus phi over kT. Okay. So as far as we can tell, taking everything we know from cosmology, it gives you a very simple way to understand the dark matter halos of galaxies. Right? Now, I haven't told you yet why some galaxies are high surface brightness versus low surface brightness. Whatever happens, you need feedback to create stars in the disk and get the right amount of stars in the right galaxies. Right? Feedback's part of a galaxy's life. You cannot avoid that. What I'm telling you is that the dark matter in this model is nailed down. Right? The final prediction for the dark matter is nailed down, and it makes it very predictive. All right, what about other models, right? I'm not a big fan of doing this because I think the model that I've presented to you stands on its own, but it's kind of interesting to ask, what does it do better than existing models? This is a little bit of a complicated plot, but let me just show you what it is. This is one specific group's SIDM simulations. So they are the Nihau simulations, right? A very successful, beautiful set of simulations. And in the background, you can see sort of the rotation curves they've generated. Those are the gray ones. And the data for a few galaxies are shown by these data points. And then the solid lines are the SIDM fits. So for now, just disregard the SIDM fits. Just compare the data to the gray points, right? What you take away from this is that already in modern simulations where the feedback is getting you the right stellar mass halo mass relation, is getting you roughly the right median sizes for the galaxies, they can make cores, right? And that's a part and parcel of the feedback process. You can see this is a big core, right? But what I would argue from this, what is going wrong, is that the feedback is strong enough not just to create a core, but it also makes the stars less, more diffuse, right? Because stars are collisionless, dark matter is collisionless. You do something to the dark matter, you probably do it to the stars too, right? And the way I see that is that, you can see that these galaxies are the ones that are not produced, right? And it's not an issue with rotation curves, it's just the sizes. You just don't make enough compact galaxies with this feedback method. So in my mind, I think this is a clue that what we have in terms of the feedback models is not quite right. And I think that's kind of exciting that it's no longer enough to just get the median properties right. You have to get the scatter right. You want to be able to explain why as George was asking, why are there high surface brightness and low surface brightness galaxies? How do you get both ends right? It's not enough to get one of the ends right?
And these are for the same range of concentration. I mean, I doubt they selected.
So as far as I can tell, they didn't, I mean, looking at the papers and asking a few people, they didn't do anything specifically different in terms of selecting the zoom-ins, that they just,
But usually when you do it, you don't select super high or super low concentration.
you don't.
So I'm
Yeah.
saying, I agree with your point that it's tough to make dense galaxies, but they probably don't have those extreme concentrations in the center.
Maybe that's the case, right? But I would say you're missing a good half of this. It's not just the lowest part here. So I don't know what the answer to this is, right? Because even in SIDM, like I told you, the only way you're going to make the very diffuse galaxies in SIDM is if they are the low concentration ones, right? So my claim would be that the concentration is intrinsically related to the galaxy properties, which is not the dominant view in terms of like, thinking about galaxy formation, right? It doesn't, people haven't really been saying that it's the concentration that actually drives things. At least for the low concentration, for the more diffuse ones, I would say, at least in SIDM, the only way to get them right is if they're born in the low concentration halos. And remember, low concentration really means they formed late. That's the interesting part, right? And so there is actually there's a predictive power here, right? If you could actually take a bunch of low surface brightness galaxies, know enough of their star formation history, and actually see when when most of the stars formed, not an easy thing to do, I think, but in principle it's possible. You should be able to test this. You should be able to test that the low surface brightness galaxies are, on average, younger than high surface brightness galaxies. All right, just in terms of like statistical fits, this is for the 100 odd galaxies you're looking at. This is the CDF of the chi-square per degrees of freedom, so just what fraction of the galaxies are well fit with a certain chi-square per degree of freedom. And you can sort of see SIDM's doing pretty much as well as you can imagine it's going to do. Chi-square per degree of freedom of 1 is about 70% of the galaxies, right? So it is doing the right thing, and the right thing is correlate the baryons and dark matter in a certain way, right? Which is when the dark matter is less dense, it's also the baryons are less dense, or vice versa, right? And this is the DC14, which is a fit to the Nihau simulations, right? And it's also, it doesn't do as well as SIDM because of that, I think mostly because of that high surface brightness end. But it does better than just an NFW fit, which is this black line. And this magenta is the MOND, or the radial acceleration relation. Right? MOND does really well at fitting the median, but it does a horrible job of explaining the scatter. Right? So if you've ever been told that MOND fits galaxies well, it's just not true. Right? It is giving you sort of the median relation, right? That's what it was built on, but it doesn't do a good job of like fitting it galaxy by galaxy. All right, I'm going to skip through this. So that was my, if you want, like this is my main motivation for you, why I gave you that model that was based on the rotation curves, because it does such a great job of fitting the rotation curves. Okay, and it's, yeah.
Just a quick comment. I mean, even in CDM, that is non-interacting with baryonic feedback, there is a relation of the half-mass radii of galaxies with the core size, which would kind of imply the same. But the question there is how to get the galaxies in that range that are compact.
I think that at the end, in all these models, that's the thing, is how do you get the galaxies, right?
But in terms of the correlation, that would be the same correlation from feedback. That the bigger the galaxy, you typically end up with bigger core of the dark matter.
Yeah, I mean, like in the Nihau, that's typically the case. Yeah, so I think it really boils down to like now getting the full range, right? And I would say the other thing is, in my view, with SIDM now you have a lot more freedom in how you build the feedback model, because at the end of the day the dark matter is going to come out right. It's not a constraint you put on your feedback models. You want to just get the baryons right, right? However you do the baryons, the dark matter will do what I just told you. And that's the neat part about this model. All right, so I cannot claim this is, at this point I'm not standing here and saying that it is SIDM and not CDM. And why am I not doing that? Because of what sort of Dushan's like referring to, which is if you don't understand the feedback within CDM, it's hard to say it's ruled out, because maybe there's another feedback model there that actually give you everything correct. And if that's the case, we need something else to break the degeneracy. And I claim that there is. Down the road, let's say we understand feedback in both of these models well enough, then the satellite galaxies will function as, as a way of breaking the two, the degeneracy between these models. And that has to do with, this curve I showed you, partly. Okay. So here's the next bit of physics, one slide that we need to know. So this curve I showed you tells you about the evolution. So just look at the solid curve first. You start out at high density in the early universe. So that's essentially like an NFW halo. As time goes on, your density decreases, right? And normally, as told you that for any reasonable cross section, you're sort of in this ballpark. But if you have a satellite galaxy and it falls into the main halo, as it orbits the main halo, it's going to lose mass. And as it loses mass, what's happening is the outer heat bath, all of the dark matter particles that were in the outer part, that was sort of the heat bath, you lose that. And so now you go through this process of core collapse much quicker. Okay? And if you haven't thought of this in this context, an easier thing to think of is, remember globular clusters. Globular clusters have a similar phenomena where eventually they go through this process of core collapse. Okay, and the same thing is happening here. Okay, slightly different reasons, but it's a similar physics. As you lose mass, this process by which you start turn around and core collapse happens quicker. Okay, and now a satellite galaxy, even for cross sections of order 5 centimeters square per gram, if you strip enough mass in the outer part, depends a little bit on the orbit, can actually go through this core collapse process, right? And the densities can be much higher than what it is in the field. Okay. And this, is something that's really unique to SIDM, because you can get densities that are higher than even in cold dark matter model, because you have this core collapse process happening.
So in all collisionless components are along for the ride, right? So stars as well, increasing the central density.
I mean, in this picture, when I'm talking about the dwarf galaxies, the stars are irrelevant essentially.
Well,
but in practice, if there were stars around, then they will follow the dark matter along with them adiabatically. Yes.
You're not going to see the dark matter, but you're going to see the stars and the gas.
Yes. So there's a
atomic mergers, for example.
so there is, yes. So again, in this case, adiabatically, when you push the dark matter in, you would expect that the stars follow along, right? And so the size of the compactness of the stars should be related to that of the dark matter. The flip side is also true. So for example, Zavala and Fogelsberger did some simulations where they showed that, as in a field, as the dark matter density gets low, since you're removing mass from the inner part, the stars just adiabatically expand, right? And so it just makes things shallow, right? So the sizes of the stars, stellar disk is set by the dark matter in that case. And so in this case, yes, the opposite should happen. All right, so let me try to just show you one plot of this, and then I'll go to the summary. So here's an example of what happens in a satellite. So this solid line is the CDM. As you increase the cross section, what I want to show you is that, this is for a particular orbit, where instead of the density going down, you see this for cross section of order 3, this density in the satellite is actually higher than CDM. In fact, if I jack it up to 10, and 10 is totally reasonable, nothing rules this out, okay? Because this is a small velocity. It's completely core collapsed. And eventually this portion of it, if nothing else stops it, is going to turn into, some fraction of this will turn into a black hole. Right? And the time scales are fairly quick for that to happen. So it really just depends on the cross section, right? So there is this other prediction within this SIDM model, which I know surprisingly no one's really sort of worked out, which is that you expect a spectrum of black holes. Again, depends on the concentration, depends a little bit on how what the orbits are, but that's there. Here's another orbit, and the difference between this and this is concentration. This is a high concentration halo, so it formed pretty early. This is a low concentration halo. It's low concentration, so the time scales are pretty long, and you never get to this core collapse process. So as time goes on, as you can see, the density just keeps going down from 0 to 3 to 10. So in SIDM, you can get a huge amount of diversity. You can get these like really compact 1/r² profiles, and you can get this huge cores. Right? And that's, once we understand this, and we are able to sort of like, compare this to the CDM predictions, I think this provides a pretty unique way to like try to like distinguish them. All right, let me just, all right, maybe one more slide. These are not just true for like satellite galaxies. They would be also true for these dark subhalos that people have been looking for, both in gravitational lensing and through effects on the stellar streams in the Milky Way. So for example, there is a detection with GD1 stellar stream. And here's an example from Simona Vijay's work, her first detection of a dark subhalo. And neither detection has been shown to be really consistent with CDM. They're in fact very compact. And maybe this is a signature of core collapse. I don't know, but what I'm trying to tell you is that there are, in principle, differences between SIDM and CDM when you're thinking about satellites and subhalos. And that might be the way to break the degeneracy between the two models. All right, so let me just put this up and say that the simple model that I presented is an excellent description of dark matter halos, consistent with all known observations. Nothing rules this out. Okay, I'm trying very hard to like break it. As of now, it hasn't broken. And I would say, as of now, it does explain phenomena that cannot be currently explained within the CDM model. Maybe this will change. I don't really know. But what I'm really excited about are the last things I told you, that there are concrete avenues to falsify it using satellite galaxies. And hopefully in a couple of months, there will be sort of this online review. So this is supposed to be a living review. There's a similar living review on sort of dark energy that's already out, led by Bhuvnesh Jain. You can go to novelprobes.org. So there will be a similar review on SIDM, just putting together all of the different ways in which SIDM affects small-scale structure, galaxy formation. Right? So sorry for going over this.